Hi everyone, myself Dr. P. Ashok Babu. In this video, I am going to discuss about the magnetic flux density and Maxwell equations. Magnetic flux density and Maxwell's equations. So first of all, same as the electric flux density, we can define the magnetic flux density. So here the magnetic flux density B is similar to the electric flux density D. So we know that the electric flux density D is equal to epsilon naught E in free space. The magnetic flux density B is related to the magnetic field intensity H by using the equation where the magnetic field intensity B is equal to the magnetic flux density B is equal to mu naught into magnetic field intensity H. B is equal to mu naught into H, where mu naught is the constant which is known as the permeability of free space. Where mu naught is a constant which is known as a permeability of free space. Here the constant is in henries per meters. Henries per meters. We have the value mu naught equal to 4 pi into 10 power minus 7 henries per meter. So here the magnetic flux through a surface S is given by similarly same as the electric flux. Here we can define the magnetic flux. In electric flux we have defined it as the electric flux psi is equal to surface integral d into ds. Similar to the electric field intensity. So here we can define the magnetic flux. The magnetic flux through a surface S is given by psi is equal to surface integral b into ds, where the magnetic flux psi in Webers and the magnetic flux density is in Webers per square meter. Weber per square meter, or we can call it as a Tesla. So here we can observe the figure. So the magnetic flux lines due to a straight wire with current coming out of the phase. So here the dot convention is, so here the convention, here there are two types of magnetic field conventions, a dot convention and cross convention. So if it is a dot, the current will flows outside. If it is a cross, the current will move towards the inside. So this is the difference between these two, dot and cross convention. So here the magnetic flux lines due to a straight wire with current coming out of the phase, because it is a dot, the current will come outside. So it is a flux, magnetic flux lines. This is a magnetic flux lines around a magnetic field. So here if an electrostatic field, let us assume an electrostatic field, in an electrostatic field, the flux passing through a closed surface, the flux passing through a closed surface is the same as the charge enclosed. According to Gauss law, we have the flux psi is equal to integral d into surface integral d into ds, which is equal to the charge q. So thus it is possible to have an isolated electric charge. It is possible to have an isolated charge like this. So it is an isolated charge. So due to the isolated electric charge, so here because it is some closed loop, here the charge enclosed equal to the flux linkage in that particular charge. So here let us assume a point charge plus q. So due to the point charge q, so the lines may be here, the flux lines are like this. So here the flux in electric field, the flux starting at the one end may end at the other end or may not end at the other end. So here in electric field, please observe this. So in electric field, the flux starting at the one end may end at the other end or may not end at the other end. Whereas coming to the magnetic field, the flux starting at the one side, it should end at the other side. So this is a basic difference between electric field and magnetic field. In electric field, the flux starting at the one end may end at the other end or may not end at the other end. Whereas coming to the magnetic field, the flux starting at the north pole should end at the south pole, or the flux starting at the south pole should end at the north pole. So this is a basic difference between the electric and magnetic fields. So here thus it is possible to have a isolated electric charge in electric field. So which also reveals that the electric flux lines are not necessarily closed. It means that the flux starting at the one end may close or may not close at the other end. So unlike the electric flux lines, the magnetic flux lines always close upon the other end. Or the magnetic, it means the magnetic flux starting at the north pole should end at the south, or the magnetic flux starting at the south, it should end at the north pole, like that. So therefore, because of this reason, it is not possible to have an isolated magnetic pole in magnetic charges. So it is not possible to have an isolated magnetic charges in magnetic fields. So here we can observe this one, magnetic fields, there are different magnetic fields. So it is a magnetic field. Here the flux starting at the north pole, it is ending at the south, or the flux starting at the south pole, it is ending at the north pole. So here because of it is a closed surface, the flux psi is equal to 0. The flux psi is equal to 0 in the magnetic field. Whereas in the electric field, because of the isolated charge, the flux psi is equal to the charge enclosed in the particular surface. So because here the flux is ending at the other end, the total net flux equal to 0 in magnetic field. So here we can observe the different magnetic fields. So it is a successive division of a bar magnet. Bar magnet results in a pieces with the north and south poles, showing that the magnetic poles cannot be isolated. The magnetic poles cannot be isolated. So here it is a first one is a total magnetic field, which is having the south and north poles, which is divided into 2 parts, which is divided into 4, which is divided into 8 parts. So in each and every part, we can observe that there is a north pole and south pole. The flux starting at the south should end at north, or the flux starting at north should end at the south pole. Therefore, an isolated magnetic field is not possible in magnetic fields. Isolated charge is not possible in magnetic field. Therefore, because there is no isolation charge, the total flux in any closed surface is equal to 0. Therefore, thus the total flux through a closed surface in a magnetic field must be 0. Therefore, we can express it as a surface integral B into ds is equal to 0. Surface integral B into ds equal to 0. So this equation is referred to as a law of conservation of magnetic flux. This third equation 3 is known as law of conservation of magnetic flux, or which is also known as Gauss law for magnetostatic fields, which is also known as a Gauss law for magnetostatic field. Here if you apply divergence theorem to the equation 3, here if you apply divergence theorem to the equation 3, here the divergence theorem will convert the surface integral into volume integral. Therefore, surface integral B into ds equal to volume integral del dot B dV is equal to 0. Therefore, from this equation we can write that del dot B is equal to 0. Del dot B is equal to 0. So this is the fourth Maxwell equation, or second Maxwell equation for magnetic field. This is known as a fourth Maxwell equation, or second Maxwell equation for magnetic fields. So here as a summary, we will see the all Maxwell equations. So here the Maxwell equation in differential form, the Maxwell equation in integral form, and there is some remark. So all these 4 Maxwell equations are for Maxwell equations for constant field or static field. So these are the Maxwell equations for static field. Maxwell equations for static field. So first we will see the first equation, del dot D is equal to rho V. Del dot D is equal to rho V. So in integral form, it can be expressed as it is a surface integral D into ds equal to volume integral rho V dV. So which is known as a Gauss law. Second one, del dot B is equal to 0. So del dot B is equal to 0. In the integral form, it is surface integral B into ds equal to 0. So this is also known as non-existence of magnetic monopole. Just now I have discussed about that. So there is no separate isolated charge. There is no isolated charge in magnetic field. Therefore, we can call it as a non-existence of magnetic monopole. So from this, you can observe that there is a non-existence of magnetic monopole. Next, third equation is del cross E is equal to 0. Del cross E equal to 0 means it is a line integral E into dl is equal to 0. Del cross E is equal to 0, which is in integral form, line integral E into dl equal to 0. So which denotes that the conservative nature of electrostatic field. The equation 3 denotes that the conservative nature of electrostatic field. The fourth one is del cross H equal to J. So del cross H equal to 0 means so line integral H into dl, line integral H into dl equal to it is a surface integral J into ds. So which is known as a Ampere's circuit law. So these 4 equations are Maxwell equations for static field. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.